Hello, everyone. Welcome to SciSpectra's webinar on natural fractures characterization from open holes. My name is Patricia Rodriguez. I'm a petrophysical and geoscience advisor with more than 25 years of experience in petrophysics, rock physics, and reservoir characterization. Before we start, I want to give you a very brief introduction about our company. I know some of people that have been connecting. I know them from a long time ago. But for those of you that do not know SciSpectra, we are a software consulting and training company. In consulting, we provide consulting in several areas of geoscience, but we like to group our services into 4 areas. In each of them, we have a niche that we call, in which we have developed proprietary tools to do consulting. Some of them are actually commercially available, and some are not. So this area, one of them is fracture characterization and modeling. In particular, the two, I would say, like big niche topics for us are the generation and calibration of fracture-related attributes and fracture statistics from seismic. Second one is in the regional petrophysicals modeling section. We have tools to do fast normalization of large regional data sets. We're talking about thousands of wells. In this case, we also have tools to do regional mineralogy and estimation of porosity and fluids. In the area of lithology characterization and modeling, kind of putting everything together to calculate species probability and reliability from seismic. We have proprietary tools for that as well, and use those to do seismic constrained geological modeling. And last but not least, fracture conductivity modeling and recovery optimization, putting together the concept of geomechanics to calculate faults and fractures conductivity and reactivation, and calculate fracture permeability models. And you can actually, if you go to our webpage, you're going to see that we have several what we call calculators. That one of them is stress polygons, some to calculate effective permeability. Those are concepts that are done in, of course, in a smaller scale in the calculators, but we apply those to actually large data sets. In the area of training, we have construction of fracture reservoir models for flow simulation, incorporating geology, geophysics, and geomechanics. The talk that you're going to see today is actually part of this training. This training has been done with the SDG, given through the SDG, EA, AGE, the PTTC, and to several private companies. We also have a petrophysical multimedia analysis class that's been done mostly through the SPWLA, but also having given to private companies. We have actually 2 upcoming sessions, one in English, one in Spanish. You can find more about that in the SPWLA webpage. It has been given to 180 people in the last 3 years. And we have the last one is the one about seismic, which is from fundamentals to advanced applications and model building. We usually give this one only to private companies that have requested us the service. It's for mainly aimed to geophysicists with less experience, or actually also geophysicists of any, with any amount of experience that would like to learn more about other areas of geophysics. So we go through all the way, explain the fundamentals, and we get to the more modern applications. If a lot of people from geology and engineering like to take the class, so they can learn more about how all the seismic is used and incorporated into modeling. So let's start right now with our talk. This is, as I said, natural fracture characterization from open holes. I want to name our collaborators, which are Chris Sam and Reynaldo Michelena. They are some of the main instructors of the fracture characterization class. So let's start talking about how do we build a reservoir model for flow simulation. So we have several we call like pieces of information to build it. We start with the metrics model, then we have the natural fractures model, and then the geomechanical model. All that gets incorporated to be able to do the flow simulation. As I said, this is what we talk about in the class. So in part of the natural fractures model, we have to go through, I'll call like the petrophysical characterization of the fractures. So how the petrophysicists can help with this analysis? How would we incorporate our knowledge into the natural fractures modeling? So the role of petrophysicists in the analysis of fracture reservoirs, I would call it, beyond what we do for the metrics property. How do we talk about that? So there is one piece about characterization. So we analyze the logs to identify fractures and extract intensity and geometric information. And we also analyze the logs to identify the presence of fractures that can later be used to identify the phases that are prone to fracturing. But our job, it doesn't end on this first, I would call it, first pass of characterization. So we come with the logs and we say, well, this is where the fractures are. Then there is a piece at the end in which we call it the calibration and integration, in which we integrate the information from logs to define those phases that are prone to fracturing that we mentioned in the first step, but that can be mapped using geomodeling techniques. It's not only saying that these are the phases, it's how we can map them now with or without seismic. We also integrate the log and production data to help that identification of fractures. And when the fracture data is not available, we can help to define conceptual models to identify phases prone to fractures. And at the end, also calibrate the results. We integrate everything. We kind of start going in a loop to understand that all the work has been done. So what are the objectives for today? We're going to discuss the use of log data to identify and characterize natural fractures. We're going to present logs that are commonly used to help interpretation of natural fractures, discuss the pitfalls and limitations of the different techniques, and discuss the limitations of estimating fracture porosity from logs. So let's talk about fracture identification and characterization with logs. Fracture characterization with wireline logs can be quantitative or qualitative depending on the data available. Image logs are the only truly quantitative measure of fractures. They give intensity, dip, and strike, while the other logs just provide indicators of fractures. Characterization of fractures with non-image logs is typically based on what we call indirect physical effects caused by the presence of the fractures. The robustness of the fracture information from logs depends not only on the data available, but also, and more importantly, the quality and of the consistency between the measurements. Okay, because we have observations with, I would call it one log, and we have in other, if we see something that in other logs as well, if there is consistency, and you can see in for example, mud logs, that gives you a good sense that the data that you're analyzing is corresponds to the presence of fractures. So, as I said, in reality, all log measurements are indirect measurements, but some are more, I would say, like they have a closer look to the fractures than others. So what we call the direct measures is the most direct measure of fractures is the optical image log. Then we have the sonic or resistivity-based image logs, and a little bit, moving towards the indirect information, we have the cross-dipole sonic. Then in the other end, we have what we call like the normal quad combo, actually not the triple combo type of logs, like the PE, density, the resistivity, and the caliper. The resistivity, depending on how the resistivity was logged, it can give you a little bit more indication than the other logs. And in the middle, we have mud logs, sonic, and temperature. It depends on the quality, but they are usually, when used in combination with other logs, they are good, and also good with tools for calibration, outside of the interpretation. So how we do the fracture identification and characterization with logs. We have this table here. I'm not going to read the entire table. We're actually going to go and discuss the topics of them. But this is going to be in the recording, so you will have availability to it. We start with image logs, and that's how I divided the information. We have optical, resistivity, and sonic. In this table, what I'll specify here is what you can learn from each of the logs. What are you really measuring when we talk about indirect measurements? If you keep in mind that this is what you are really measuring, it will help you to make sure that what you are seeing are fractures or not. And also the potential issues, either to acquiring or not the log, or actually how you can confuse the measurements with something else. So we're going to start with the image logs, then we're going to jump to the cross-dipole sonic, which is a tool that many people use to identify fractures. And then we'll spend some time discussing how can we learn something about fractures using just regular, everyday triple combo or quad combo logs. So let's talk about image logs. Image logs are wireline tools that provide a high-resolution optical, electrical, or acoustic measures of the borehole. These are some of the acronyms. They are described here. There are probably many others depending on the service company. They scan the surface of the borehole and provide a picture of the irregularities in the wall. They actually provide a very reliable measure of fracture geometry, dip, and azimuth. It is actually, you're going to see the pitfalls is actually a bias, but reliable measure. They provide a localized, reliable measure of fracture intensity. You can know how many fractures you have. And they may provide information about fracture connectivity, if they're open or versus closed, if they're bed bound or through going, like both. So there are the three types of image logs. We start with resistivity-based. These are paths touching deformation. The image shows stripes with partial coverage. They're pretty good depending on also because depending on the borehole size, you get a more complete or coverage of the borehole. They have issues when you have resistive mud or when you have a lot of flow of oil to your borehole. The acoustic-based tools, which are actually, I said, my favorite tools because they are rotating tool with a centralizer, so they provide a continuous 360 degrees images. One of the issues that people, I say, like don't like about this kind of images is that you cannot see like cemented fractures. For the typical applications that I use the fracture logs, I care more about the open fractures because we're looking for flow. So I probably won't be able to see the cemented ones, but I'm looking really to look for the open ones. So it's usually very useful. And we have, of course, the optical base. It's also a continuous 360 degrees images. They provide this unwrapped digital picture of the borehole wall, which kind of sometimes people call it like a virtual core. They can provide free images if the borehole fluid has to be completely clear. And that's one of their limitations. So what are how do you identify fractures from image logs? And I know probably many of you here attending today are very familiar with this, but this is for all audiences, so I'm gonna go through some of the basic things. So the image, it looks like it's the unwrapped image of the borehole. So when you have a fracture that is near vertical, it would look like a sinusoid in your borehole. So basically this is, in this case, north, east, south, west, and it comes back to north. But if you have horizontal logs and you have vertical fractures, this vertical natural fracture will look like a straight line. So you have to keep in mind that when you're looking at the image log, you have to keep in mind the geometry of your borehole as well. You can get many features from image logs. As I said, natural fractures appear as sinusoid. Stratification looks horizontal when you're in a vertical well. If you have drilling-induced tensile fracture, they are parallel to SH max, and they are typically just vertical, kind of pseudo-vertical lines. Borehole breakouts are perpendicular to SH max, and they look. You have to have what we call it the two images of the breakouts. And they're very useful for you to understand the stress state of your area. In the case of horizontal wells, we have natural fractures appears as high dip straight lines. They are when the well is oriented perpendicular to the fractures. A stratification in this case will look sinusoidal, and we have examples here. This is actually the stratification. You can see the drilling-induced fractures can be vertical. They are not shown here, but the best displacement can help identify faults. And you can see that here, these three red arrows here show how there was a displacement on the stratification, and it's an indication of faults. And you can see also an example of bed-bound fractures that they are open. You can see them here, and that they stop at the bed boundary. How this analysis of the image logs is reported in many different ways. This is just an example in which the vendor provider, the lithology, they provide usually an image of the one of the versions of the image log. In this case, is the resistivity one, and they have the tadpoles, in which indicate, give you information about the dip and the strike of I would call it of the feature that they're analyzing. In this case, you have a stratification with the 0 degrees dip, and you have the fractures actually 90 degrees. They're close to vertical fractures, and they provide a fracture intensity curve, which is kind of a window counting how many fractures per foot you're gonna, in this case, per meter you have. They also provide this, we call it Rose diagrams. In this case, they are partial. They can be provided standalone, or they can call the pole diagrams as well, in which they compile everything, and it gives you information about dip and strike and azimuth of the fracture. So let's start talking about some of other issues, other aspects of the image log. So if you have this information, you get 95 out of 100 cores will not contain a fracture, and 88 out of 100 wellbore image logs will not contain a fracture. Would you consider this to be a fracture reservoir? You know, when only like 15% of your, I call it 15 to 12% of your observations have only have natural fractures. We have asked this question to many people in our classes, and the majority of the people will answer no. This is not a fracture reservoir. I mean, you see some fractures, but it's not a fracture reservoir. In reality, this is a picture of the reservoir that we're talking about. So this is an outcrop, and this is the amount of fracturing of the reservoir. They're actually 10 to 15 feet of spacing, so it's highly fractured. So the problem with this observation is the bias on the sampling. So let's talk about that in limitations and pitfalls of image log. One of them is sampling bias. So you undersample fractures that are parallel to your wellbore. So you have vertical wells will always underrepresent the near vertical fractures. It's what we call a deep bias. In our horizontal wells, you will overrepresent the vertical fractures, and you will have a deep and azimuth bias depending on how the fractures are with respect to your wellbore. Some areas are better sampled than others, just due to the well coverage and distribution. And just a fraction of the reservoir fracture network is really sampled. So we are really, in comparison to when you want to distribute fractures in the reservoir, you are only sampling, you're only investigating a little bit. The other pitfall, and we'll talk about a little bit more about these limitations in detail in a little bit, is the aperture overestimation. They're affected by the borehole condition and doesn't represent the average aperture of the fracture. And of course, the interpretation pitfall. So let's talk about, and in this interpretation pitfalls, we have subjective bias, inconsistency of image log interpretations between wells, misclassification of fractures, like open versus closed, bed bound versus through-going. And when the fractures and the bedding are parallel, there are sometimes difficulty separating them. So the linear sampling bias and the Terzaghi correction factor. What this means is that, as we mentioned, if you have a vertical well and you have these two intervals with the same in fracture intensity, you'll see only one fracture with your vertical borehole, while you're going to see 10 fractures with your horizontal borehole. So there is a Terzaghi correction that is a formulation between that is proportional to the angle of the fracture with respect to your borehole. The way it works, and I'm not going to go into details of the math, of course, but it's depending on the fracture inclination with respect to the borehole, which is this. So this is the fracture dip, And the boreholes, in this case, we have the vertical is the dark blue, the horizontal is the light blue, is the intermediate blue, and the 45 degrees is the light blue. The correction factor changes. So if you have a vertical fracture in a vertical fracture 90 degrees in a horizontal log, the correction is 0. So you just multiply by 1 your intensity. But if you have vertical fractures in a vertical borehole, you have the maximum correction, which is 8.2, or it's an angle of 83 degrees. So this correction is applied, and it helps to really understand better the intensity of your fracturing. So this is an example of the fracture frequency before and after correction in a vertical well that had vertical fractures. So you have the red was your uncorrected intensity, and the blue is after correction. The horizontal well, on the other hand, did not receive too much correction. You have the red here, and the blue is just a small correction, because, as I said, it depends on the angle and not necessarily the fractures are 90 degrees, perfect 90 degrees. So there is still some correction to be made. So let's talk about aperture from image logs. And the aperture is really important because many people you need the aperture information when you're doing a fracture reservoir model and you distribute natural fractures. The way to calculate fracture porosity, you're going to see that it's related. You need the aperture as a parameter, how much porosity you have there. So it almost always, the image log will overestimate the aperture. And the reason is because the fractures are from image log are affected by roughness and washout. And also, the fracture aperture varies along the fracture aperture varies along the fracture. So you have, you can be reading something here, but in reality, we know this is not a perfect plane. So whatever number you see is not, it doesn't represent the aperture of the entire fracture. With the washout, you can see here the example from the optical borehole. You can see how at the face of the wall of the borehole, you can see how you have bigger holes that are probably doesn't represent the entire, really the reality of the fracture. When we think about interpretation pitfalls, is that we have wells like this that you can see these are the interpretation given by the provider. And you can see that there are many other features that are not interpreted. Even actually here, you could probably see bed bound features. This is the stratification boundary, and they were not interpreted. So it is important for you, when you receive image logs interpretation, to look through them and look for at least consistency. Because one of the issues that happens sometimes too is that, especially if you have boreholes that are really long, and there is a lot of work to do the image interpretation, there is some, the interpreted, even, I know they are doing their best job, but sometimes they get tired and some features they get not interpreted, or you have different interpreters between different wells, and some have different criteria. So what you're looking for is really to have consistency between the wells. Okay, so now we're gonna move topics out of the image logs, and we're gonna talk about the sonic amplitude log. So I'm gonna play sound for you, so just pay attention and tell me which, well, you don't have to tell me, but just listen to it and try to discern, and I will tell you later, which of these dishes is the broken one. I'm gonna play it again. Okay, hopefully you were able to discern that there was one of the plates that had a different sound. And if you want to share that in the chat, it's fine, but I'm gonna tell you right away. So to do that, great. I see a lot of B's. Somebody said A. Majority of people said B. Okay, you were right, the crack was in dish B. And there was a closed crack that is really hard to see. We had a rupture that you can hardly see here in this picture. And what happened with that crack is that when we did we recorded, as you know, we recorded this, and we did a frequency spectrum, and you can have the amplitude versus frequency, and you could see that the broken one, which is the black curve here, had less amplitude. So it had some attenuation due to the presence of that crack. And this blue here is actually the average of the three other dishes. But if you compare them to each of them, they are all very similar to this. So you could see that there was attenuation of the high frequencies in the broken dish. So why I bring this here? It's just that sonic waves respond to fracturing, I would call it in a very specific way, and that's what is very useful when you are doing fracture analysis. Sonic tools, they measure the speed of propagation of the waves through the formation. Unlike nuclear tools, which measure what we call atomic particles, sonic waves are sensitive to the microstructure or texture of the formation. The microstructure of the rock has effects both in velocity and amplitude. And this is what you were hearing when you look at the dishes. Okay, you have the wave, you know, as I said, with the other logs, it doesn't necessarily matter too much where the atom is placed in the rock, but in the case of the sonic tool, and also in the resistivity tool, you have the waves, you know, they are moving towards through the formation, and they can see things that not the other tools can. So you have, for example, you can measure velocity and amplitude and isotropy. That's what the cross dipole sonic does between fast and slow shear waves. So if you have this, in this case, in the right hand, this idealized picture of fractures, you send a wave, and what is happening is that it splits, and you get a shear wave that is slow when it tries to cross this, I call like planes of fractures that are open. By the way, they have to be open and have something inside to create this anisotropic effect. And you have the fast shear that moves parallel to them. So basically, when you have the wave just going through the rock, it moves really fast. When you have the wave having to cross through the fracture features, it starts to slow down. And so the only other thing that you have to consider here too is that there is also what we call effects of, and I'm going to go this back here. There are also effects of stress, because the stress, when you have SH max and SH min, and especially you have a lot of anisotropy, so a lot of difference between your shear, your horizontal stress between the minimum and maximum, the structure of your rock changes too, even if you do not have fractures. So you are going to see also splitting of the shear waves between the two directions. So there are more advanced cross-dipole sonic tools that include what we call dispersion analysis and can help you identify the cause of anisotropy. They are not, I call like, they're called, I forgot the name, tools, I won't try to say it right now. But there is a difference, as I said, between the slow speed or slowness between the two directions. But you're going to need to do further analysis to understand if that is due to anisotropy or due to fractures. Sorry, the anisotropy is due to fractures or to stress anisotropy. This is extremely important. A lot of people just jump right away when you see anisotropy and conclude that these are fractures. You need further information to know that, or unless you are sure that you are in an anisotropic stress situation and you don't have to worry about those effects. The cross-dipole logs, I call it displays. This is one of them in which you typically have I call it slow and fast shear waves displayed, and the difference between the two is what they call the anisotropy. The anisotropy, actually, sometimes they report both type of anisotropy in the amplitude and anisotropy in the slowness, and you should look at both. You can see the waves here. Not everybody does that, and also I call this the amplitude map of the cross-dipole. So what are the limitations of the cross-dipole tools? Is that you need additional information to explain the cause of anisotropy if there are stress of fractures, as I mentioned. They can provide good orientation. They will provide, the strike. They don't give you deep or intensity, but intensity sometimes, if you are, feel comfortable saying that anisotropy is due to the presence of fractures, you could combine you can say that the amount of anisotropy is due to it's proportional to the intensity of the fractures. As the other limitation is that assumes a single family of vertical fractures or like near vertical fractures. If you depart from this assumption, it may yield erroneous results. For example, orthogonal system of fractures, that they are in all directions, can be extremely permeable, but it might be missed in the cross-dipole zone. So let's talk about other wireline logs to identify fractures. Is the most indirect measurements of fractures. The identification of fractures is based on what we call disturbances of the signal, which means that understanding the typical response or character of the log is required to identify this disturbance. It is sufficient for fracture identification when you see the disturbances on several logs. Typical logs are resistivity, density, caliper, mod log, PE, temperature, etc. An example is that if you see washouts in a tight interval and you have severe mod losses, that's a good indicator of fractures. But you need to have more than one indication. Fractures are seen primarily on tight intervals. When porosity develops, we don't see the fractures, even though you may be in a shear zone. I will touch base on that topic again at the end when I give a couple of examples of how to integrate the information. And these other wireline laws can allow to identify facies prone to fracturing and represent an indirect assessment of fracture intensity. I would call it very indirect. I mean, there are not many instances where you can you can qualitatively say that some areas are more fractured than others. You probably cannot completely map them. These facies prone to fracture can be mapped when multiple wells are present. And an example of that, this is a work we did in a carbonate. We see here the description of the template that you're going to see in the next one, that we have the caliper here in yellow, we have the gamma ray, we have the density, what we call the original and modeled. So the original is the red curve, and the model one is the yellow, and it looks like yellow black dash here. This, what we call facies here, it was a matrix facies characterization. When we start having these nulls, it was just because the points were really away from any of the facies that we were training. So it was also an indicator that something was wrong, I would say. And the resistivity, we have resistivity deep and shallow. I think this was a lateral log. And you can see what I call it like a short circuit type of indicator. But it's important to know that the mud weight and the mud type affects borehole integrity and development of the washout. What it means is that it might be that you have several wells close to each other and you see the washout in the same facies of the same rock. You see this, what I call disturbances of the signal that you can attribute to the fractures, and you don't see them in the nearby well just because the mud system was better designed to avoid problems with the borehole. Because what happens is that when you have a very highly fractured interval, it just basically crumbles depending on the mud that you have. In the same interval, we look at the mud log, and we see here that we lost circulation, and we actually did not have samples returned. So we have a couple of indicators that in this well help us to calibrate the signature of the fractures. And then with that, when you look at several wells nearby, you could always identify that section of the borehole. There were sections like this in which we didn't have any issues with the density. So you didn't have disturbances of the density. You just had that, like to call it a short circuit resistivity signal. But because of what you saw in the nearby wells and the calibration with the mod log, you could, I would call it, confirm or feel comfortable saying that this is also a facies that is prone to fracturing. These facies flags are used then to map fracture facies across the area. What are the limitations of using other wireline logs to identify fractures? First is that you need to understand the reason for the perturbation. That's crucial. Disturbances in one single log cannot be used to reliably identify fractures. It requires information from different log types to be useful. Doesn't provide information about geometry, deep on azimuth. If disturbances are found in different logs, we can conclude that fractures are present, but the contrary cannot be affirmed. So basically, if you see this fracture signature in multiple logs, yes, you can say that they're fractures. If you don't see them, you really just don't know if they're fractures or not. So it's kind of only one way in one direction. So you can see them, but if you don't see them, they are maybe there and you just were not able to see them. This kind of plots in which you integrate, we call it like montage, when you put several different logs and you can calibrate using, in this case, we had information about fractures and orientations. We had mod logs, and similar to the other one in which you put all your logs and you calibrate with different information, helps you to feel comfortable about your conclusions of how to, of which facies are the ones that are prone to fracturing, or that they'll have the more fractures than others. So fracture porosity from logs. In most reservoirs, fracture porosity is very small and therefore is overwhelmed by the matrix porosity. Exceptions are the igneous and metamorphic rocks where no matrix porosity exists. So fracture porosity is usually estimated using reservoir modeling, and it is related to intensity. Hence the importance of calibrating fracture intensity. Some techniques claim, and I said claim, they can measure porosity from wireline logs, but they are just more really fracture indicators, and we're going to discuss the sonic versus neutron density porosity to estimate secondary porosity. Fracture porosity, as I said, is too small when in the presence of matrix porosity to be measured with wireline logs. So the fracture porosity, when you have some matrix porosity, becomes really kind of more in the noise of the tool. But if you are sure that there is no matrix porosity because of the type of rock you're in, you can definitely conclude that whatever porosity you are measuring is really due to fracture. So fracture porosity from wireline logs, the sonic secondary porosity index. The theory behind it is that, as I said, the sonic travels through the solid rock. And it tries to avoid the fractures. And I'm not talking now about the cross-dipole sonic, just the regular sonic. So you have the sonic, it always is going to look the path of least resistance, so that the rock is going to look harder than if you, it's going to look harder than what it is. So theoretically, when you compare the sonic porosity to the neutron density porosity, the sonic porosity is going to be lower. And the difference can be attributed to fracture porosity or to other kind of, I call it structural, that is not measured by the sonic. But it has an important assumption, is that the matrix porosity calculated with the density neutron will be the same as with the sonic, which means that we're talking that this is valid only for what we call the Wiley rock type, because the porosity from sonic log uses Wiley's equation. And if you are familiar with the field of rock physics, you will know that the rock physicists have spent many years trying to model the wave of the sonic wave, basically the slowness, in this case the dt, and it's much more complex than Wiley's equation. So Wiley's equation is only valid in certain type of rocks, like for example a very clean carbonate, like a limestone. You could probably estimate a good porosity from Wiley's, And if you compare then that to the density porosity, the comparison, you can say that those are a probability of fractures, let's say. So you have to be very careful with that. It can provide you some other information, but it's typically just that the modeling of porosity using the sonic versus using neutron density is just different. So to calculate fracture porosity, we typically do it using reservoir modeling, and the fracture porosity, the aperture multiplied by the length and the height divided by the total volume of your, what we call it, the U cells in your cellular model. I said the aperture is typically calibrated from production tests. As I said, using wireline logs, image logs to estimate the aperture is usually overestimating it. So we do a calibration loop in which you, after you are comfortable with your distribution of fractures because you calibrate it with logs and seismic and any information that you have to I call it tune the amount of fractures that you have and the size, then you work with the aperture and the reservoir engineer to tune it until you feel you can reproduce the production, and you can do a production match if you have production. If not, you may have to do several scenarios. And with that, you just calibrate the aperture, and therefore you can estimate your porosity from fractures. So with this, we're almost getting towards the end, and hopefully we get a few minutes for questions. As I said, the petrophysics role in the characterization of fracture reservoirs has two ends, one in the characterization, the understanding of the logs, and one in the calibration and integration. And we're not talking in this talk about calibration and integration much, but I'm going to show you three plots in the next three slides as an example of the things that we look for, and they vary, I call it, enormously between different projects. But there is one plot that we always show in our classes, and this was built more than 10 years ago, and still we find it very, I call it, very practical, and the observations have remained constant across, along the years. Is that this is a neutron density cross plot. You can see here the three lithology lines, the sandstone, limestone, and dolomite. And we have like three, quick facies polygons, the porous limestone, porous dolomite, and what we call brittle rock or tide. And this tide, in this case, this is a conventional reservoir. So the porosity was, what we consider tide, was less than 8%. And 94% of the fractures, so this is colored by the fractures that came from the image log. So we just, it's log data in the two axes, colored by the information from the image log interpretation. And we are showing only conductive and partially conductive fractures from the SMI. And 94% of them appear in less than 8% porosity. This observation, we have seen it, again and again in different reservoirs. It's extremely consistent how the porosity, the majority of the fractures are found in rocks less than 8%. We have another example here with carbonates and sandstone in two different projects that's different from the one in the previous page. And this is fracture density versus matrix porosity. And again, we see that how the fracture density drops after you reach the 8% threshold. And this seems to be constant between sands and carbonates. The previous slide was in carbonate. What is interesting too about these observations is that unconventional reservoirs are typically found below that threshold of 8%. And we tend to believe that the unconventional reservoirs are not fractured. And really what happens, and this is, I call like a topic of discussion between many professionals, and we are in the group of the ones that believe that the unconventional reservoirs are actually fractured reservoirs. It's just that those fractures are not open, or what we call not active. They don't flow on their own like many other conventional fracture reservoirs do. And that's why the hydraulic stimulation helps so much in the production, because when you do the hydraulic frac, you are stimulating and you're changing the pore pressure, and you're activating all these natural fractures and allowing the flow. There's, of course, you are opening a hydraulic fracture too, and that helps to the flow. And there are many other ways that the conventional reservoir gets stimulated. Here is another example of how we integrate and calibrate seismic and petrophysical properties. In this example, we observe a good correlation between seismic properties, in this case strain and curvature, and open natural fractures, but only intervals with low clay content. In the first track, we can see how the block curve, which corresponds to the intensity of open fractures, correlates nicely with the curvature in red and the strain in black. We see the increase here at the top and the decrease where we have the closed fractures here in orange. While in the lower part of the section, there is a high strain and high curvature area or section where there is large clay content and therefore no fractures. With this, we conclude our talk. Thank you very much for your attention. For more information, please contact us via email at info@scispectra.com or visit our webpage, scispectra.com. Have a nice day.